Okay, in this lecture, we are going to be going over independent samples, the write-up portion for the final project. And we've got two independent samples. We have Texas and we've got California, and we're going to take a look right here at this yellow box to tell us what it is that we're looking at. This data allows you to compare the average salaries for occupations in Texas compared to the average salaries in California. So the first thing that we're going to do is we are going to run the descriptive statistics from the data analysis tool. Now I went ahead and I ran everything, so but I'm going to still rerun pretty much everything again. So what we need to do is we need to go to the data tab on the top, go to data analysis, and when you go to data analysis, click on descriptive statistics, press OK, input range. You're going to highlight the entirety of the input range, okay, grouped by column, and the labels are in the first row. And then we're going to put it into an output range, and I'm going to scroll up, output range, and I want the output range to start right here, which I know I already have it all there, but I'm going to put it in there anyway. And I'm going to ask for the summary statistics. I'm going to ask for the confidence level for the mean. Now, this is really important. We need to make sure that for the confidence level for the mean, put in there the value that corresponds with the alpha value. So if you're going to use an alpha value of 0.1, which that's what we're going to use, put in 90% because an alpha value of 0.1 corresponds with 90%. And then I want the maximum value and I want the minimum value. And so this is everything that I want for the descriptive statistics. I'm going to press OK. It says output range will override. Are you okay with that? Yes, I'm okay with that. And bada bing, bada boom, it gives me everything that I need to know about Texas. So this right here is Texas. And then this is everything here is for California. So let's go into here and determine what it is that that we're going to be running. Tail. Do we expect the salaries in Texas to be lower or higher than California? Notice I say it in that very specific direction. Texas comes before California. So how does Texas compare to California? Are the Texas salaries going to be lower? Are they going to be different, or are they going to be higher than the salaries in California? And the answer is they're going to be probably lower. Next question. Am I going to use a z, am I going to use a t, or a chi-squared? And you know what? I'm going to actually go with a t. And the reason why is because technically if it's under 200, just run a t. It's going to be more accurate. And then the declared alpha is 0.1. So in other words, I am willing to have a 1 or a 10% chance of error. And then the degrees of freedom. How do we calculate the degrees of freedom? There's two ways to do it. The first way to do it is you add up to the two of these. We've got the count of Texas and we've got the count of California plus 168, and that's 252. And then you do 252 minus 2 equals 252 minus 2, and that is one degree of freedom that we could use. So we could use 250 degrees of freedom. But why does it say 194? And we're going to get to that in just a minute when we get into the assumption testing. So for right now, let's leave this blank and we'll come back to that. So sample 1 mean, you'll notice we've already got the sample 1 mean right there. Sample 1 standard deviation, sample 1 size, we took that from right down here. And then we've got the sample 2 mean, and the sample 2 standard deviation right down here, and then the sample 2 size. Okay, so the next thing that we need to determine is what is the research question? What is it that we want to know? And notice I have a lower tail test. So what I want to know is, are the average salaries in Texas less than the average salaries in California? Notice my research question already implies direction. Next, same thing with purpose for running the test. In order to determine the purpose for running the test, what I'm going to suggest you do is come down here to independent reference, and this is on the final project example sheet, but it's got all the purposes right here. So you can look at these purposes and you can see, okay, which of these purposes are the purpose that I'm running right now. Determine if there's differences between two independent groups. Determine if there's differences between interventions, between change scores. Examine the difference between the means of two independent samples. These are really actually the same things. So I'm going to go to independent and I'm going to say, okay, I'm going to examine the mean of Texas to determine if it is statistically significantly less than the mean salary in California. And what am I anticipating? I'm anticipating the average salary in Texas will be lower than the average salary in California. And once again, notice all of these are implying a lower tail test. Next, what is the one dependent variable, and is it measured at the continuous level? So the dependent variable is salaries, and I actually, just because I'm so kind, I actually have the dependent variables written right there for you. Just make sure that you understand why these are dependent. The dependent variables are the actual values that are in here, and these values are dependent on these categories. Okay, these values are going to change based on what these categories are. So the dependent variable is salaries, and they are continuous. Some of you will have like counts and whatnot, which those are technically discrete, but when you start averaging them, when you take averages of counts, then they become continuous. Okay, what's the one independent categorical variable consisting of two categories? So the independent variable is state, and it is categorical. The two categories are Texas and California. Next, are each one of these independent of one another? And the answer is yes. Just because you have one salary over here, it's not going to impact anything else. Texas is going to impact these salaries. California is going to impact these salaries, but nothing else is impacting these salaries. Next, we are going to look at a few assumptions. Assumption 4, there are no significant outliers in the two groups. So in order to determine if there's any significant outliers, what it says right here is make a box and whisker plot to the right. Note information about the outliers and describe your visual interpretation of the box plot. Okay, so I'm going to come over here and I'm going to delete this box plot for right now, and we'll come back to that. But let's see here. So let's make a box and whisker plot. In order to make a box and whisker plot, we are going to highlight all of the data, and we're going to go Insert, and we're going to click on this, and click Box and Whisker. Okay, and I'm going to cut that. I pressed Control X, and I'm going to just move it over here. Press Control V. So now I have this box and whisker plot. Box and whisker of TX and CA salaries. And notice I'm putting Texas before California. I'm always putting Texas before California. I'm going to add data labels to the left. I'm going to add a legend to the right here. Now, your box and whiskers may not look right like this. Some of them are going to have a lot of outliers. Some of them are going to have like the box and the whiskers are going to be all the way down here with a ton of outliers above it. I have a whole video just on that, on how to deal with outliers. So make sure that you watch that. But for this, we're going to take the max value, which is going to be 123,589. Okay, and then quartile 3, which is right here. We're going to do 78,636.25. And there's another way that you can do this too. Here, let me show you the other way. Equals quartile inclusive. And I'm going to highlight the array. So I'm going to highlight Texas. Oh, and then I want the quartile, I want the median. Okay, so it gave me the median. Okay, so we've got the median right there. And what's really cool about this, we're going to press Control V. We're going to get quartile 1, and then the minimum value, that's not an outlier. The nice thing, because there are no outliers, we can do the exact same thing. And then do 1. And then for the mean, we can do equals average. And because we already have the entire data range right here is C12 to C95, we can do the average. And then outliers above, 0. Outliers below, 0. And you'll notice it's all the same values as what's right here. It just, actually, it's slightly different. These values are excluding, and these are inclusive. So it depends on how you run it. These values right here are just calculating it slightly differently, but it's relatively the same thing. Nothing that you need to worry about. It's just methods, what methods you're going to choose to use. So same thing with this. Let's do the max value. So equals max, and we're going to highlight the entire range again. So let's highlight the entire range. Okay, so we've got the max value for that entire range. And so we're going to copy this, Control C, and then we're going to do equals quartile inclusive, and then we want quartile 3. Okay, and then we want the same thing, Control C, except now we want the median. And then we want quartile 1. And then we want the minimum value, that's not an outlier, which since there are no lower outliers, you can do the same thing again of 1, or sorry, of 0, because 0 is going to give you the minimum value. And then the mean, once again, equals average. We put the range in there. And then outliers above, there's 0 outliers above, 0 outliers below. And there's a way to count the number of outliers that are above. I'm going to show you that really quick. I'm going to say equals count if, and I'm going to put that range. Remember, having that range is great. Count if in that range, okay, if the values are greater than, let's just do the number of values that are greater than the median. So if it's greater than, and put the greater than in quotation marks, and then put an and symbol, greater than, and then you click on the median, and this right here is set up to tell you the number of values that are greater than the median. So there's a total of 84 values that are greater than the median. Okay, let's see how many values are greater than Q3. Okay, there's 42 values greater than Q3, and if I were to say how many values are greater than the max value, it's going to be 0, which if you want to include it, what you could do is you could say outliers above. You could put an equal sign here, but we don't really want to put an equal sign there, so because we want outliers above it, so we don't want the equal sign. And so yeah, that's how you would do that. So moving on, that gives you all of those values. So if you're not able to decipher the values, which for a lot of you won't be able to, that will show you how to do that very easily. Next, let's look at creating a histogram. Well, before we do that, let's we want to write this right here. There are no outliers. There we go. So we made a box and whisker plot. A box and whisker was made for both categories of Texas and CA. And then we're going to look at this and see, okay, and we're just going to kind of describe it. Okay. Both distributions had 0 outliers, and the quartiles appeared to be relatively uniformly distributed. In other words, what I mean by relatively uniformly distributed, these quartiles are all pretty similar. Okay, yeah, I know that these ones are a little bit higher, but these are pretty, relatively similar, and not too extreme by any means. Okay, so moving on, the next thing that we want to do is we want to make either a histogram or we want to make a frequency polygon. And for this, I would actually much rather you make a frequency polygon. The downside about making a frequency polygon is it is just a little bit harder. Okay, because in order to make a frequency polygon, what you have to do is first make a frequency table. So we're going to make a frequency table really quick. So I just highlighted this data, and now I'm going to do insert, pivot table. So I selected the data, and then I'm going to put it into an existing worksheet, and I'm going to put it below this right here. So below the write-up section, that's where I'm going to put it. And so I've got this nice pivot table, and I'm going to put Texas and Texas values. Okay, now I actually had already set these up into groups, but don't forget, when you do this, what I'm going to do, I'm going to go ahead and ungroup it. So design, let's see, ungroup. So this is what it's going to look like. And now I'm going to click on it, and I'm going to say, okay, I want to group it. Okay, and I want to start at 20,000, because that's a nice round number, and I want to do it by 10,000. So this right here, we've got this wonderful, these are the number of salaries in Texas, the number of salaries in Texas for each of those values. Okay, and then let's also do California. Okay, and so we're going to put California there, and once again you're going to have to do the same thing. You're going to have to group this one again, but because I had already done it, it just automatically did it for me. So I'm going to copy this, Control C. Oh, I forgot to put the actual, oh no, we're good. And so you're going to run into a small problem here, and I'm about to tell you what the problem is. Because these are not even, let's see here. Because these values are not even, when you make the chart, it's not going to look quite right. And I'm going to show you what I mean. So I'm going to say insert, and we're going to go to, there we go, frequency Polygon, and so I'm going to change the series names. Let's see here, select data, edit, series name, this is going to be Texas, and then this is going to be California. Okay, now this is all well and good, and it looks great, and you're like, okay, that makes a lot of sense. However, the problem with this particular frequency polygon is that California has twice as many as Texas. So you might actually want to do a relative frequency polygon, and you would get a lot better results. Okay, and how do you do a relative frequency polygon? That's a really great question. Well, if you want to do a relative frequency polygon, all that you'd have to do is add one more column, And when you add the one more column, you say summarize values by, let's see, or sorry, show values as percent of the column total. Okay, so we're going to copy this, Control C, Control V, and then we'll do the same thing for Texas. Count, and then we're going to instead of count to, we're going to show values as percent of column total. And then we're going to copy this, Control C, Control V, and then 0, 0, 0. There we go. And now we will do Texas, California, and we're going to make another frequency polygon, insert frequency polygon, and you'll notice now it's a lot different, right? So let's take a look at the comparison of these two, and I don't know about you, but to me these tell a different story. The one on the top basically represents the relative frequency polygon. Although they look almost identical, the one on the top basically takes away the problem that we have with the sample sizes being different. And so if you're going to write a more honest chart, or if you're going to make a more honest chart, in my opinion, this one right here is a much more honest chart. So comparison or frequency polygon of Texas versus CA salaries. So you can definitely make a frequency polygon like this, and in my opinion, like I said, this is probably the best option. But if you don't want to make a frequency polygon, if you'd prefer to make two histograms, you can make two histograms instead. And in order to make a histogram, it's really easy. You just highlight the data, and you do insert histogram, and it gives you a histogram, and then you're going to have to write Texas salaries. But I don't like this, and the reason why is because the bin width, you notice the bin width, the overflow bin, the underflow bin, it's hard to control this, where with the other one I was able to control it a lot more, and so with this it's just harder to control what it looks like. So Texas salaries, and then I could make California salaries in another one. So insert histogram, and so now I've got the California salaries, and so Texas salaries, California salaries. And so both of these are technically correct, but I hope that you guys can see that even though both of these are technically correct, the frequency polygon is by far the better option to use for the independent samples test, because you are very much so specifically comparing two distributions. And even more so, the relative frequency polygon is the better of the two, not just a frequency polygon, but the relative frequency polygon. Because when you compare California to Texas here, I think that you guys can agree that this right here provides a lot better insight. And so what we would do is we'd come over here and we'd say, okay, we've got the, let's see here. We're going to make a histogram. So we made the histogram. And I'm gonna Control X. I'm gonna put this right here for a minute. Okay. A relative frequency polygon was made Okay, so a relative frequency polygon was made to visually compare the distribution of salaries for both Texas and California. This is really just to determine, do these look really different? Yes or no? Is there something that's really concerning that you see here? And really, there's nothing concerning that we saw. So you say both categories appear to be close to a normal distribution and did not appear to be skewed. But no worries, we can actually test whether or not they're skewed. And there's a few different ways that we can test it. First of all, in our fun little descriptive statistics, we come over here and we can actually see, here's the kurtosis, here's the skewness, and you notice the kurtosis is negative 0.4389 for Texas, and the kurtosis for California is negative 0.307. And then the skewness for Texas is 0.4279, and the skewness for California is 0.470846. So because these are all under 1, or all within 1 standard deviation of not being, not being skewed or not being platykurtic or leptokurtic, we can determine that this data is normal, that it's normally distributed. Okay, and so that's something that I had actually already written right here. So I'm just going to cut this, and I'm going to put it in this explanation right here. Alt-Enter. And I'm going to say, as the skewness and kurtosis for both independent groups are all less than 1 standard deviation away from being perfectly distributed, the data is considered to follow a normal distribution and does not violate this assumption. Okay, and so I'm going to do something... There we go. And so coming right here, there we go. We've got the skewness and the kurtosis. We've got the actual values written right there. And then we've got the interpretation right there. Except I accidentally put this in the wrong Control X. It's supposed to be right here. I was wondering where that went. Okay. Next, F-test. The sixth assumption is that the variances of the two distributions have to be relatively similar. In other words, one shouldn't be, extremely spread out while the other one is very compact. How evenly spread out is this data? And so in order to determine that, there's a few things that we need to do. The first thing that we're going to do is we are going to run what's referred to as an F-test. Okay, and you come all the way down here, and there's a little spot where you need to put the F-test. And so what we're going to do is we're going to do data, data analysis, and then we are going to do F-test for 2 samples for variances. And press OK. So variable 1 range. So we're going to come up here, click right in here for variable 1 range, and we're going to highlight the data for variable 1. And then variable 2 range, we're going to highlight the data for variable 2. We're going to say that there is, that the labels are in the top. And then the alpha, we want the alpha to be 0.05. This alpha has nothing to do with your alpha that you chose for this test. This is an alpha to determine statistical significance for homogeneity of variances. Okay, so output range, we're going to put the output right here, and then we're going to press OK. It's going to say, oh, do you want to go over it? And the answer is, yeah, I'm fine with that. So this F-test, you'll notice that it has an actual F value. This is the F value. And if you wanted to, you could actually go to an F chart, just like a T chart, just like a Z chart, just like a chi-square chart, and you could determine the probability of getting this F test with this number of degrees of freedom. Or you could just take a look at this p-value right here, and you'll notice that this p-value, this 0.0366, this p-value indicates that the probability of this occurring, assuming that they are identical, is less than 4%. Okay, so what we're going to do is we're going to say F equals 0.7029, and then we're going to say P equals 0.0366, and we're going to copy this, and we're going to bring it up here. Okay, and notice it says right here, if we run an F test with one tail, it's going to be 0.0366, or if we do it with two tail, it's going to be 0.073. Now there is another way to do this, and in this middle part right here is all the Excel formulas that you can use. So you can actually use an Excel formula, and so if I were to use the Excel formula and I were to do equals f.test, and I were to highlight the first array, okay, and then I highlight the second array, which I highlighted the category names too, so I don't know if that's going to make a difference. There we go. So it gives me the probability of a two-tailed test, or if I were to divide that by 2, it gives me the probability of a one-tailed test. And so it's really easy to run that even without the descriptive statistic or the data analysis tool. So make sure that you pay attention to these in the middle. They're really phenomenal to use. And then I have an entire worksheet down here that goes over exactly, what each one of them does. Okay, so this was violated. In other words, because the probability is so low, the assumption is violated, and because the assumption is violated, we actually have to run our test a little differently. So we are going to run our test 2 times. Okay, the first time we are going to be running our test assuming equal variances between the two groups. Okay. The second time we are going to run the test assuming unequal variances between the two groups. So we're going to run the Ttest to compare the independent samples between Texas and California, the independent samples of salaries. Okay, so I'm going to go data analysis, and I'm going to do Ttest assuming equal variances. Press OK. Variable 1 range. Okay, and then variable 2 range. I'm going to highlight all of variable 2. And then the hypothesized mean difference is 0. Labels, we did highlight the labels. And the alpha, remember we want the alpha to be 0.1. And then for the output range, click on output range and click exactly where you want it. So we want the Ttest for 2 samples assuming equal variances. We want it right here. And we're going to press OK. And it's going to override it. And then we're going to be able to see all of this information. Okay, and notice it says degrees of freedom is 250, hypothesized mean, pooled variance. This part is actually really important. We're going to get to that in a little bit. Then we've got the actual variances, the means, so on and so forth. So notice then it also has the probability for a one-tailed and for a two-tailed test. However, this is assuming equal variances. we have to assume unequal variances. So we're going to run this test one more time. We're going to go data analysis, and we're going to do Ttest 2 samples assuming unequal variances. Variable 1 range, which I wish I would just carry it over, but variable 1 range. Then variable 2 range. Hypothesized mean difference is 0. There's labels. The alpha is 0.1. And then the output range, we're going to put the output right here. And then press OK. It's going to override all that. And now we have the t-test for 2 samples assuming unequal variances. And remember earlier I said, hey, the degrees of freedom is 194. There's this formula that's in your textbook. It's rather cumbersome, that basically says when you have unequal variances, this is how you need to calculate the degrees of freedom. There is basically, when you have unequal variances, when you adjust the degrees of freedom and make the degrees of freedom lower, it makes your results and your interpretation a little bit more conservative. It says, hey, this data isn't perfect. This data is violating this assumption. This data is not perfectly, both sets are not, perfectly distributed in tandem with each other. So because of that, we're going to make a slightly more conservative interpretation. And so we're going to have degrees of freedom of 194 degrees of freedom instead of the 250 that it could have been if they were the same, if the variances were the same. Okay, so we've got all that data to the left. Excuse me. Technically, we have run the entire test, but now we're going to go through the null and alternative hypothesis. Okay, so we've got the null and alternative hypothesis. The null hypothesis says the mean of, which if you want to know a little bit more about how to write these up, go to independent reference, and you'll see right here, this is how you write up a 2-tailed, this is how you write up a 1-tailed. Okay, and so we're going to go back to independent, and the mean of Texas is greater than or equal to the mean of California. That's the null hypothesis. Basically saying there is no difference between the mean of Texas and California, but if there is a difference, it's going to be the opposite of what you think it's going to be. Okay, and then the alternative hypothesis is saying, hey, this is what we're expecting to happen. The mean of Texas salaries are going to be less than the mean of California. And once again, you notice this arrow is pointing in the lower direction, so this is going to be a lower tail test. A lower tail test. Okay. And then right over here, you can just write out in words what it says. Next, the test critical value. The test critical value, which I meant to do this. There we go. Automatic. Because you guys can write about this. But the test critical value. There's a few ways to determine the test critical value. And what I'm going to encourage you to do to find the test critical value is I'm going to encourage you to use one of these formulas because it's much more accurate. Okay, so I'm going to do equals t dot inv. Now, is this a 2-tail or a 1-tail? This is a 1-tail. Okay, so what we're going to do here is we're going to say we want a probability of 0.1, so that's your alpha, and the degrees of freedom of 194. And we're going to see that the test critical value is going to be negative 1.29. And let's see if 1.2859. So let's do negative 1.2859 is the critical value, and it's just much more accurate than using the table. Not only is it much more accurate, it's just so much faster. And so you've got this t.inv, and you can just put that, put your your degrees of freedom and your alpha level in there, and you're good to go. So just be aware of that it's a lot faster and it's a lot more accurate. And if you wanted to, let's see here, just keeps going and going and going until all the way to 9. And so what we're going to write here is using the t.inv, the alpha of 0.1 and degrees of freedom of 194, we determined that the t crit value is negative 1.2859. Okay, and so that is the critical value. Okay, so reject decision rule. We're going to reject the null hypothesis if tcalc is less than negative 1.2859. And let's see here. I just wrote this out. If the calculated test value of the average Texas salary compared to the average California salary is less than negative 1.2859, then we'll reject the idea that there's no difference between Texas and California. And so that's what this decision rule is saying. And then you can literally just copy this, Control C, and then press Control V. If the calculated test value of the average Texas salary compared to the average California salary is greater than or equal to negative 1.2859, we will fail to reject the idea that there's no difference between the two. Okay. There we go. Between Texas and California. Next, what is the test calculated value? In order to get the test calculated value, we are going to just come down here to the t-test for two samples. Should we do assuming equal variances or unequal? Well, because the variances were not equal, we need to use the unequal variance. So we're going to use this right here, negative 3.87. So we're going to do negative 3.87, Control C. Negative 3.87. So the average salaries in Texas are 3.87 standard deviations below California when considering the salaries of Texas and California. Okay, what is the probability of this? Let's see here. Here is the probability of this occurring. Okay, assuming that the salaries of California and Texas are the same, this is the probability of the result that we just got. So we're going to write this up and we're going to say the probability of having this particular result, assuming the null hypothesis is true, is less than 0.01%. Okay, so you'll notice P is less than 0.0001. I don't ever want you guys to write P equals 0. I always want you to write P is less than 0.0001 or something to that effect. Okay, so even if it says P equals 0, just write P is less than 0.0001 or something like that. Okay. Next, are the results statistically significant? In order to determine if the results are statistically significant, you need to compare the p-value to the alpha value. Okay, the alpha value, remember the alpha value is 0.1, the p-value is less than 0.001, and so therefore the results are statistically significant because the p-value of less than 0.01% is less than the alpha level of 0.1. So therefore the results are statistically significant. So make a hypothesis decision. We need to compare the t-calc to the t-crit. And so basically, because t calculated value of negative 3.87 is more extreme or less than the t critical value of negative 1.285, then the p-value is that's all that we need. We reject the null hypothesis because the t-calculated value of negative 3.87 is more extreme than the t-critical value of negative 1.285. Okay, then the difference scores between the samples. Texas salaries on average are $12,847.85 less than California. This is the difference. This is like you caught something, you noticed, hey, this is the difference that we got. Okay, great, we got a difference. This is really important to note, and you really need to write, hey, this is the difference. Okay, next, we've got the standard deviation of the sample for Texas. And so we've got the mean plus or minus the standard deviation. And what we're able to say here, and the way that we did this is I did equals, and I came over here to the descriptive statistics, mean minus standard deviation. Okay, then I did equals mean plus standard deviation, and you'll notice right down here you've got this standard deviation right there, but the actual limits are 39,000. You notice 39,324, 39,324. 68% of the salaries in Texas fall between 39,324.56 and 85,840.15. So these are the limits, and I can tell you that 68% of the salaries fall between there, or else you could also write it like this: 62,582.36 plus or minus the standard deviation gives you the range of the standard deviations. Also with the confidence interval, and once again we have these wonderful formulas. So when you go over to your descriptive statistics, remember we did our descriptive statistics, and with our descriptive statistics we calculated the 90% confidence level. And remember I told you use the 90% because you are going to be using that alpha. And so because you did that, you can actually just use these instead of calculating it again. And so what we're able to do is we're able to do equals mean plus the confidence level, then equals mean minus the confidence level. And so you've got the lower level of the confidence level, confidence interval, and you've got the upper level or the upper value of the confidence interval. And what we know is that we are 90% confident that the actual population mean of California salaries is between let's Control X, Control V, 71,890.21 and 78,970.2. So that's what we're able to determine with this information. I'm just going to delete that. And so that's really good information, right? So based on the sample data, we are 90% confident that the actual mean salaries in Texas somehow that got mixed up. So we are 90% confident that the actual population salaries in California are between 71,000. So California, that's actually supposed to be down below. Control X, and we'll do Control V. And then we'll do the same thing for Texas. Okay, so we will do equals mean, equals the mean minus the confidence level, and then we've got equals the mean plus the confidence level. And so we've got the confidence levels right there, the upper and lower limits of those confidence levels. I'm just going to put it right there, and just the values. So I'm going to say, I'm going to copy this, paste it right here. We are 90% confident that the actual population mean of Texas salaries is between 58,361.21 and 66,803.51. Okay, and so we've got the 90% confidence intervals, and then we also have the standard deviations showing us where 68% of the data falls between. And so we've got a lot of information, and last but not least, we're going to write this up. So I'm going to pause this for a minute while I write this up. Okay, we are going to calculate the effect size really quick. So the effect size, remember the effect size is basically, we went on a fishing trip, and let's go through this really quick. We went on a fishing trip, we described where we were going to go on the fishing trip right up here. Okay? Tell me what you're fishing for, tell me what you're considering to be a catch. Next, what are you looking for on your fishing trip? Research questions, so on and so forth. Then check, are you at the right lake before launching? Are you at the place where you're going to be able to find the results that you're looking for? Don't go to the lake that you want to catch a walleye, but they only have perch. Don't go to the lake where you want a lake sturgeon, but they only have bass. Make sure that you're going in the right area to be able to find your results. Next, you caught something, you got a significant result. Really great that you got a significant result. So happy for you. And so we can see right now you've got the significant results. You've got the test calculated value. You've got the probability value. But the question is just because you got all of that information, does it actually mean anything? And the truth is it really doesn't mean anything until you find out, okay, how large of an effect size is this? How noticeable is this difference? Yes, you might have a difference, but do you have to have statistical techniques in order to be able to see that difference? And so then we've got some descriptive statistics there to kind of outline that. But if you come right up here, let's take a look at the effect size. Okay, and I'm going to delete this. And we're going to put, in order to calculate the effect size, or the practical significance, or how noticeable this really is just to the average observer, we're going to take the mean 1. So we're going to do equals mean 1, okay, equals mean 2. And then remember that pooled standard deviation? There's a couple ways to do it, but the easiest way to do it is to come right down here to where it says Ttest for 2 samples assuming equal variances. Okay. Where you see pooled variance, in order to get the pooled variance, it's right there, or you can do, if you need the pooled standard deviation, you do equals square root for the pooled variance. Okay, so we've got the pooled variance, we've got the pooled standard deviation. What is it that we need up here? We need the pooled standard deviation. So we're going to press Control V, do just the values, and I'm going to get the pooled standard deviation. Control C, Control V, and this is the formula that we need to put in. Okay, so equals this minus this divided by the pooled standard deviation, and that gives us an effect size of 0.487, or what's really close to a medium effect size. So if we have a significant result with a medium effect size, the actual difference would be somewhat noticeable, but it's not huge. Okay, so down here, the difference between Texas and California, the results are that it's somewhat noticeable, but it's not huge. Okay, it's not something that you're like, hey, this is massively huge. And so when we write this up, we're going to have to write it up and say, hey, we can notice these results, but we need to know that it's not a massive difference. It's something that should be noted, something that's definitely noticeable, but it's not huge. Okay, so we're gonna, we wrote this up. So what was run? An independent samples t-test was run. Okay. Comparing what? Comparing the average salaries in Texas and the average salaries in California. Okay, the average salaries in Texas are $12,847.85 less than the average salaries in California. That's the result. Okay. The probability of this occurring, assuming there is no difference between Texas and California, is less than 0.01%. Okay, there's the p-value. Give insight about the possibilities of why this occurred. The probability of this occurring, it is possible that the cost of living is also higher in California. California. Let me fix that. Salaries reflecting higher costs of living. We are, and then after that, talk about the confidence intervals and standard deviations, whatever's appropriate. We are 90% confident that the actual average salary amount in Texas is between 58,361.21 and 66,803.51, and the average salaries for California is between Okay, and then as these two confidence intervals, notice that this confidence interval does not overlap with this confidence interval. And that's really what we're talking about here. If they don't overlap, then we know that they're going to be different. Okay? And as the two confidence intervals do not overlap, we are very confident that the Texas salaries are less than the California salaries. Furthermore, the results are fairly noticeable with an average sample size, and the results of the tests are practically significant. These results can be used to provide practical insight. And so this is essentially the entirety of what you need to put together for this portion of the project. Hopefully this was beneficial to you. There's lots of information. So, just keep working at it, and I hope that this is beneficial and that you're learning a lot. Thanks.